Okay, so we still need to cover section 7.2, but I wanted to do this little discussion with you because it relates to section 5.7. When you have solutions to differential equations that are complex, you extract your real solutions from those complex solutions. And I think you should understand why that's true. This will come up if you take differential equations math 282 in the fall. Incidentally, I'm teaching that class in the fall. Um, and so let me give you a moment to copy this down, and we'll discuss it, this concept here. Okay, so let's try to give some perspective here of what we have. So remember in section 5.7, like if you look at like example 3, section 5.7, okay, where they're dealing with a circuit there. Okay, so you get two complex solutions. And of course, as you know, you only need one complex solution to a system of differential equations to find out what the real solutions are. So for instance, in this example 3 from section 5.7, the solution to their system of differential equations is the eigenvector I2 times e to the -2 plus 5i t. Okay, and this here is an example of a complex solution. And here, you can write this as e to the -2t. Sorry, one moment, one moment. Okay, sorry everybody. That was, you know my brother. He likes to call during. All right. Okay. So e to the 5t, you can write, that's Euler's number. You can write it as cosine of 5t plus I times the sine of 5t. So you have this eigenvector I2 times e to the negative 2t times the sum plus cosine of 5t plus I times the sine of 5t. I mean, you've done this many times. And basically, from this complex solution, you can rewrite that complex solution as the sum of a vector that has real functions in it plus I times a vector with real functions in it. We call that, so sometimes we call that x real and x imaginary. It turns out, remember, when you write your complex solution that way, it turns out that the x real vector and the x imaginary vector are both solutions, and I should say they're both real solutions of our system of differential equations. And you should know why that's true. Okay, you should know why that's true. So let me show you why. Okay, on the next page here, what I do is I say, okay, let's assume that this is a solution, x real vector plus I times x sine vector. Let's assume it is a solution to the differential equation. Okay, that means that x prime of t has to equal a times x of t. Or in other words, the derivative of x with respect to t has to equal a times x of t. Right? That's absolutely true. So we're told in this problem that we do have a complex valued solution. Here it is. And I'm going to differentiate that complex valued solution. Now, the derivative of a sum is the sum of the derivatives, right? Let me just, one moment here. Let me put that I back. The derivative of a sum is the sum of the derivatives. The derivative of the sum of two vectors is the sum of the derivatives of those vectors. For the second part, this imaginary I, that is with respect to t, that's treated like a constant. So we can pull the I out front here. Now, hold on here. This here is reflected as a, so a times x of t would be a times the x real vector trying to make this look good. plus I times the xim vector, the x imaginary vector. But you can distribute the A. You can distribute the A to both of those parts, and that's going to give you this here. So you see, what you do is this. What you do is this, and this is all in the recording. You look at this derivative vector. I'll circle that in red. And you look at this derivative vector. I'll circle that in blue. This derivative vector has to equal A times x real. And this other derivative vector, well, I want to be careful here. Let me hold on. Let me do this again. Hold on. I want to. Everything's fine, but let me just do this again. So this derivative vector would equal A times x real. This derivative vector here must equal A times x imaginary, because you're taking a complex vector, this complex vector here, and it's equal to this complex vector there. So the components have to be equal. It's no different than if you said A plus BI equals 3 minus 4I. You would have to say A equals 3 and B equals -4. That's what you'd have to do, right? What we're doing here is no different. The statement 1 here implies, of course, this. And statement 2 here implies this. And this shows then, that these x real vector at the x real, let me just, maybe I'll put it in green. The x real vector and the x imaginary vector, which is the vector whose coefficient is I, they are also solutions to the differential equation, but they are real solutions. You see, you can't graph a complex solution to a differential equation if it's modeling a particle that's moving around along some elliptical path in two-dimensional space. That is, a two-dimensional space is real space. So you need to have, therefore, a linear combination of two real solutions to describe the general solution for that models the motion of that particle. And naturally, if you're given some initial value, you can then find out exactly what the solution is. Are there any questions on this idea? Are there any questions at all? Okay, Cameron's good, wonderful. Yes, I agree, David. It is nice. I mean, and now, and Mikhail, like I said, if you've had Math 282, I know since I'm coordinator actually for that course, I know that you solve systems of differential equations and get complex solutions, and then just pull out the vectors you need. And you just probably kind of did that. And if you take Math 282, you just say, okay, well, that's the algorithm, that's what you do. But because you understand linear algebra, you now know why it's true. You know why it's true. So if you have to take Math 282, when you come across that material, which is usually towards the end of the course, you now understand why that process works. Okay, very, very good. If there are no questions, I will go ahead and stop this recording. Okay, great, great.